So, when almost is not even close, remarks on the approximability of HDTP. What you're going to see in the next, I guess, rather 12 than 15 minutes. Can everybody hear me? Okay, that's a clear no. Okay, second try. What we're going to see in the next rather 12 than 15 minutes, I guess. First will be a quick brush up on parametrized complexity and approximation theory. Then I will give you an intro to the Rutherford Analogy framework called Heuristic Driven Theory Projection. And then we will have a glance at some of the complexity aspects and approximability aspects relating to this framework. So, and a quick heads up, this talk actually connects to my second talk tomorrow afternoon. So here you see more the technical part. Tomorrow afternoon you will get more the ideological part. Okay, quick brush up of parametrized complexity theory. Parametrized complexity theory just is complexity theory with a little extra, namely the idea that, okay, maybe complexity theory does not properly serve fields like AGI and cognitive science because it just considers the general problem case. In parametrized complexity, what you try to do is you try to get a tool for considering problem-specific properties. Namely, you try to introduce parameters which allow you to encode certain parts of your input. So what you're seeing here is a definition of a parametrized decision problem. Namely, you have the same thing as a normal complexity theory, plus you grant yourself a parameter which allows you to codify some other aspects of the problem besides the input side. If you're now doing this, you can also expand the notion of tractability to fixed parameter tractability, which means that, okay, presume that you keep the parameter constant, so presume that you keep some of the properties of your input constant. What is the complexity of the resulting problem? If we break this down to cognitive problems, what you actually try to do is, okay, maybe humans are good at solving traveling salesman problem because they are never faced with a version where you have to connect 100 nodes. So can we maybe get a traveling salesman version where we just keep the number of nodes or some other property low and then see whether it all of a sudden becomes tractable? Of course, there are complexity classes as well. For our case, the most important one will be W1. W1 basically corresponds to NP in classical complexity theory, although this is a very rough analogy. And the class I showed before, FPT, so fixed parameter tractable, corresponds to W0, which would be P. So W1 not equal FPT can be seen as analogous to P not equal NP. It's not a straight correspondence, but it gives you kind of the idea behind the thing. On the other hand, approximability theory basically considers how well you can approximate a problem solution. So instead of trying to fix parameters, what you're trying to do is being good enough. You don't want to be perfect, you just want to be good enough, which is another notion that very frequently comes up in cognitive contexts. Here we will be dealing with PTAS, which is the class of problems that allow for a polynomial time approximation scheme, namely an algorithm which, given any arbitrary approximation ratio, returns you another algorithm which solves the problem in polynomial time. And we will be dealing with APX, which is constant factor approximation, namely an algorithm which solves the problem up to a certain bounded approximation ratio. So if you're doing bin packing, maybe you cannot solve it precisely, but maybe you can solve it up to 5% of the optimal number of bins. Okay, heuristic driven theory projection in 3 minutes. We're talking about computational analogy making. So what we're trying to do is we try to find analogies between domains which are given in a first order logic formalization, namely in finite theories. You will see an example on, I think, the next or the following slide. And how do we do this? We do this by anti-unification. So anti-unification is the counter concept to unification. What you actually try to do is you take two formulae and you try to find the least generalization over these two formulae. Of course, if you can do it for two formulae, you can as well do it for two theories, finite theories, and you obtain a generalization, which later you can then use for guiding the analogy process. So source and target given in your first order logic language, you compute the generalization and you use the generalization for transferring knowledge from source to target. Anti-unification in our version is an extended form of the classical Plotkin thing from the 1970s, and it was developed in Osnabrück by Angela Schwering, Ulf Krumnack, Kai-Uwe Kühnberger, Helmar Gust, and Ute Schmidt, like 2005, 2007 mostly. And as I already said, what you try to do is you try to get the least general generalization to two theories. In order to preserve some properties, you have to restrict your formalism. So you cannot apply arbitrary operations, but what Heuristic Driven Theory Projection is doing, it uses these four operations. Namely, renamings of variables, fixations, so instantiations. You can insert arguments into formulae, and you can permute the arguments of a formula. These are just examples for it. So, for example, if you're trying to align two formulae f of variable y and f of variable z, what you do is you generalize them into f of variable x. Or on the more complex side, if you're having two statements like f prime of a b x c and f double prime of a g b c, you clearly identify as a human that, okay, there is some similarity. I'm always having the atoms A, B, and C. I'm having like a structure which embeds several arguments, so you can generalize it into f of A, B, C. And if you want to apply it now to a real framework, like take the Rutherford analogy, so Rutherford's ingenious insight that basically the solar system and the atom might be similar, I would now ask you to just focus on the facts part. So for the solar system, Rutherford knew, okay, there is a sun, there are planets, the mass of the sun is clearly greater than the mass of the planets, and he knew, okay, with something like gravity and distance. On the other hand, what he knew about the atom is that there is a nucleus which is heavier than the electrons, and he had basically the Coulomb law and some assumptions about distance. And Rutherford now figured that, okay, these things go analogous, and he later transferred the laws, like the centrifugal equals the negative gravity law, from the solar system to the Rutherford atom. But what's more interesting for us, having a look at the facts, we can generalize these facts. So you have mass sun, greater mass planet, on the other hand mass nucleus, greater mass electron. Now you align sun and nucleus, planet and electron, and you get some theory like this. Okay, so still we are here dealing with rather complex rewriting of first order logic theory. So what we did actually is having a look at the complexity of the entire thing. Clearly, HDTP falls apart in two separate mechanisms. So on the one hand, you have the analogical matching mechanism, the restricted anti-unification. On the other hand, you might have re-representation of theories, where the second part trivially is undecidable because it's just satisfaction in first order logic. So we had a look at the analogical matching mechanism and defined three different forms. The most simple one only uses renamings and fixations, so you even more restrict the operations you apply. The second level uses renamings, fixations, and at most peak permutations of arguments of functions. And the most powerful, most expressive one is full FPA anti-unification, where you apply everything that Heuristic Driven Theory Projection gives you. If you're now having a look at the complexity of the entire thing, F anti-unification is solvable in polynomial time, which is nice and neat, but this is only working with renamings and fixations, so there's no magic happening. But as soon as you add one single permutation, so as soon as you allow yourself to switch two of the arguments, you are basically untractable. So you all of a sudden are NP complete and W1 hard. And when you then have a look at FPA anti-unification, marked as number 4 here, things don't get better if you add more features. The more interesting part, which we focused on in the paper I'm talking about here, is the approximatebility. So okay, we now know that FP anti-unification is W1 hard to compute for a parameter set M and P, which tells us that there is no polynomial time algorithm computing sufficiently complex generalizations. Where sufficiently complex here means with a lower bound on the number of higher arity variables, and at the same time this tells us that we have an upper bound on the number of applicable permutations, namely we may use none. So a pretty natural question seems to be, what happens if we just consider generalizations which merely approximate the optimal solution? Does this maybe help in any way? We were lucky in that in 2007 the original inventors of HDTP already introduced a heuristics over their operations. So renamings come for free. Fixations and permutations per application cost you 1. And argument insertions, which is naively speaking the most powerful operation, always costs you k plus 1. Now we can of course use these assigned heuristic values for ranking generalizations. So what we did following a proposal by the original authors was asking, okay, can we maybe approximate the most complex generalization, which is the generalization at the same time bearing the highest information load? Frankly speaking, no, we can't. Or at least we can't constant factor approximate them. The FP anti-unification is hard for APX poly, so there is a polynomial approximation scheme for it, but no constant factor. Conclusion? Analogy making in HDTP is widely not tractable or approximable, at least for a meaningful definition of approximable. If you now take something we call the tractable AGI thesis, so a basic demand for cognitive systems to be either fixed parameter tractable or at least fixed parameter approximable, this would tell you that HDTP, although clearly being a nice system and pretty impressive in what it can do, probably will not be suitable as a basis for a general model for high-level cognitive capacities or a general cognitive architecture. And on the other hand, this type of analysis, as it allows you, due to the parametrized nature, to really figure where the complexity kicks in, we got some nice questions we want to work on in the future. So, A, can we redefine restricted higher order anti-unification in a way so as to avoid the W1 complexity and stay within FPT? Way more ambitious, can we maybe also redefine the underlying KR mechanism so as to get it out of the full first order logic undecidability corner? Yeah, so that's, I think, my 12 minutes. Thanks for your attention.
Thank you very much. Let's see if we have some questions. Okay, let's see if we have some questions for the group in general, or someone of the prior speakers. Anyone with a burning question? I know I had to turn one person down here earlier. All right, well then let's thank the speakers and attention.